This week in 241, we'll be discussing transformers. In last week's lab, we used an alternating flux to generate an alternating current. But in this week's lab, we're going to use an alternating current to generate an alternating flux. But for what purpose? Let's start by defining what a transformer is. To create a transformer, we start with a primary coil through which we put an alternating current. We then hook up a secondary coil in such a way that the change in flux going through the primary coil is now going through the secondary coil. And that's our transformer. Transformers may seem like they're just two coils sharing some change in flux, but transformers are more than meets the eye. Let's start by calculating the change in flux of the primary. We can use Faraday's law to determine this. In this case, we are applying a potential difference across the primary, Vp, corresponding to an alternating current. Rearranging the equation, we can solve for the change in flux. We will assume that all the flux going through the primary is also going through the secondary coil. Therefore, we can plug our value of the change in flux from the primary into the equation for the secondary. Finally, we obtain a relationship for the potential across the secondary that is dependent on the number of turns in both coils and the potential applied across the primary coil. Note that in order to get a potential drop across the secondary coil, the current must be alternating, because we need a change in flux in order to get an induced EMF. Let's use some example values to get a sense of what this relationship implies. Let's say we have 5 turns in our primary coil, and we apply a potential of 110 volts across it. And let's say that our secondary coil has 10 turns. Therefore, when we do the math, we find that the potential across the secondary is equal to 220 volts, which is twice that going through the primary. Wait a minute. If power is linearly proportional to the potential, and if the potential across the secondary is greater than that through the primary, that means we've created power from nothing, defying the law of entropy. Or have we? Greater potential doesn't necessarily mean greater power. You will see in this week's lab that even though the electric potential increases, the power decreases as you transfer power from the primary to the secondary, because the current decreases. Well, if that's the case, why don't we just transfer power down electrical wires using direct current? Why do we bother using transformers at all? Transformers provide us with an efficient way of changing the voltage, that is, with a low amount of power loss in the process. As you will show in this week's lab, it's more efficient to transfer power using a high voltage, so when electricity is being transferred to your dorm, the voltage can be ramped up by increasing the number of turns through the secondary coil. However, once the power gets to your dorm, the voltage is far too high for charging your iPod. Therefore, the voltage needs to be decreased by decreasing the number of turns through the secondary coil before it destroys your Apple product.